Find the surface area of the shape created by revolving y equals 1/2 x plus 2 for 0 less than x less than or equal to 2 about the x-axis. Okay? So first thing I do with this, which is the first thing I normally do in life, is I draw a picture. Sometimes there really aren't pictures available to draw, in which case my soul is sad, but I carry on with life and just don't draw a picture for that problem. So for the line here, it's going to be a line because you have a y and an x without any powers attached to them. And so when we plug in 0 for x, we'll get 2. And then it's from 0 to 2. So then we plug in 2 for x. We have 2 divided by 2, which is 1, plus 2, which is 3. So we have 2 points. We know it's a line, so we can just connect the 2. Okay? Okay. And then we're going to revolve this about the x-axis. So we're going to get something like this. Parallel perspective. That's terrible. But sort of, that is very much more abstract than I originally intended. But it serves the purpose. Okay, so now we're trying to find the surface area. So when you think of revolved shapes, you normally think of volumes. So you're thinking, well, disk method or shell method. But you really don't quite have that for the surface area. For surface area, you're actually going to use the arc length. So the idea here then is we're going to do 2 pi r. So I'll divide it like this. So look at the shape over here. So we're going to have circle here, circle here. No, that's terrible. My perspective is all off. Like that. So we have kind of like a hollow tube. I'm going to say tube. And we're going to say this r is pretty much the same as that r, but we need to find in this length here. And so what we're going to do is we're going to find 2 pi r, multiply it by some sort of small, infinitesimally small dl. And so we find out what the r is going to be, because our r is just going to be our y value. If we look over here, this will be the radius of our circle cylinder tube that we have. And so that will be y, which will also be our radius. So r will be y, which will be 1/2 x plus 2. Now dl, on the other hand, we're going to have to look for the arc length. So I'm going to say that a small amount of L will be a small amount of x plus a small amount of y, each of them squared and square rooted. So if we look over here, take this dl here, we'll zoom in. This is just part of the circle then. This is the dl from up there. We have a delta x and a delta y. And so we're going to say, all right, this is delta x squared, delta y squared, square rooted. That gives us our delta L. We'll factor out the delta x squared, and that gives us a 1 plus, I'm going to write this as dy dx, quantity squared, square rooted. And then this gives us pretty much our arc length formula that we've seen from more traditional arc length problems. So 1 plus dy dx squared, square rooted, dx. Okay, so now that we've got a whole bunch of things written up, let's rewrite our formula in a way that's a little bit more comprehensible to us. So we'll do red. Whoop. So we have 2 pi r, which we decide is 1/2 x plus 2, 1/2 x plus 2 times square root. I'm going to find what dy dx is real quick. So dy dx equals, so y equals 1/2 x plus 2. So dy dx equals 1/2. Take the derivative of 2, that goes away, it's 0. Derivative of 1/2 x, that just goes to 1/2. Therefore, dy dx quantity squared will be 1/4. Okay, now we have the information we need. We do 1 plus 1/4, because dy dx squared is 1/4. x. Maybe. Seems reasonable. Yeah. I was surprisingly good with this. Okay. And then we'll go from points, since we're doing it along the x-axis here. It'll be from 0 to 2. Okay? So now we'll simplify things. So we have, let's see, I can rewrite 1 as 4 over 4. So this will then be, so we have 2 pi over here. I'm just trying to get all the constants off to one side. So we'll have square root of 5 over square root of 4, because the denominator stays 4. The top part, 4 plus 1, is 5. Times, and then we'll do integral of 1/2. This will all be constant. So then we'll do the integral of 1/2 x, which will be 1/2 x squared over 2 plus 2x. And this will all be evaluated from 0 to 2. Okay? Change colors. Purple. So this is 2, which will cancel with that 2 up there. So we have square root of 5. We have a pi. We have x squared over 4 plus 2x evaluated from 0 to 2. So we'll keep our pi square root of 5. And then we have, when we plug in the 2, we have 2 squared, which is 4 over 4, plus 2 times 2, which is also 4. And then we minus 0 plus 0. And those zeros will just cancel out because they are zeros. And despite the number that we add together, they will remain as such. So this is 4 over 4. This is 5. So we have pi 5 square root of 5. That seemed reasonably straightforward. See what our possible, aha, it's even a possible answer. Okay, so, green. No, I don't like that green. There we go. Okay, so right here is the answer. Same thing, whoop, whoop, either one. So, backtracking to kind of see what we did, how life worked out here. So we're told to find the surface area of a revolved shape. And we're given a line, made some sort of like tube type thing that kind of flared out. Maybe a coupling, that seems good. And an adapter, yep, adapter, to like change one size pipe to another. Okay. And so to find this area, we used the formula 2 pi r times dl, where dl is that small incremental length that go along that tube, that flaring, that gradient upward. Well, we knew what our r was. Our r was the radius, which we just plug in our y value. And then we knew we could find out what the dl was, because we know that the dl, the small difference in length, will just be the Pythagorean theorem. Delta x squared plus delta y squared. We rearrange that, we get our arc length formula, we plug that in, and from there then we solve the problem. Just kind of work our way through. So this one's a little bit complicated, a little bit in depth, but not that bad. This is probably, in the first couple of semesters of calculus, it's probably the hardest type problem you'll find, involving an arc length shape type rotation type thing. So this is a good problem. I like it a lot. Thank you much for stopping by. I will see you on the next one. Take care. Bye.